segment, we're going to talk about magnitude difference and flux ratio. By magnitude, we mean the apparent visual magnitude. So we mean a small m sub v, the apparent visual magnitude, or how bright does the star appear to your eyes. And what we mean by flux is the amount of energy that is passing through a surface per unit time or per second. So let's look at a light bulb as an example. Our light bulb is radiating out into a sphere. And what we want to know is how much light or how much energy is passing through a square area per unit time. So flux, or F, is the amount of energy that is passing through a unit area, square area, per unit time. And usually we're looking at energy units of joules, and the area is 1 square meter, and the time is seconds. So let's draw a larger light bulb. So what we want to know is, let's say we have a really, really large light bulb that's like 5 feet by 5 feet. It's a very big light bulb. And we want to know how much light or how much energy of the light is passing through 1 square meter on the surface of the light bulb. So we want to know the amount of energy that is passing through per second per square meter. And that is going to be flux. Now usually we're looking at stars and not light bulbs. So let's draw a star. Let's say we have a very bright blue star, and I'm going to draw it very large. It's got an apparent magnitude equal to 0. Now instead of putting a V for visual band, I'm going to put a B indicating that it's a blue star. So the apparent visual magnitude of the blue star is equal to 0. Now let's look at a dimmer red star in the sky, and I'm going to draw it smaller. So the apparent visual magnitude of the A star is equal to 5. So what do we mean by magnitude difference? The magnitude difference is just subtracting the two of them. So let's say m sub A minus m sub B, or it would be m sub B minus m sub A. You're subtracting the two, so that's what we mean by magnitude difference. Now let's look at flux. So you look at the blue star, and we want to know how much energy is passing through this surface, 1 square meter per second. So how much joules are passing per second through 1 square meter of the surface of the star? Otherwise, the flux of the B star. Same thing with the red star. How much energy is passing through per unit second, per time, per square meter? And we call that the flux of the A star. So the flux ratio is just the ratio of the two, or the flux of A divided by the flux of B, or the flux of B divided by the flux of A. Let's look at an example. Let's reverse it. Let's say we have a dim blue star. So the apparent visual magnitude of the blue star is equal to +5. And we have a bright red star. So I drew it much larger. So the apparent magnitude of the A star in the visual band is equal to 0. So we want to find the magnitude difference. The magnitude difference would be, let's say, the apparent magnitude of the B star minus the apparent magnitude of the A star, which is a 5 minus a 0, which is equal to a 5. Now how are we going to find the flux ratio? To find the flux ratio, let's bring in a table. So here's a table of magnitude difference versus corresponding flux ratio. So all we do is we look in the table for the magnitude difference of +5, and we go across and we see that the corresponding flux ratio is equal to 100. But is it F sub B divided by F sub A? Is it the flux of the B star divided by the flux of the A star? Or is it the flux of the A star divided by the flux of the B star? It turns out that if you're looking at the apparent magnitude of the blue star minus the apparent magnitude of the A star, in other words, m sub B minus m sub A, then the answer is going to be that you're looking at the flux of the A star divided by the flux of the B star, and that is equal to 100. Or we can write this another way and say that the flux of the A star is 100 times the flux of the B star. So the A star, which is the red star, has 100 times more energy coming out that same square meter per second. So it's 100 times more energy coming out, or the flux is that much higher. Let's look at another example. Let's say the apparent visual magnitude of the blue star is now -10, and the apparent visual magnitude, let's say the apparent visual magnitude of the B star is -5, and the apparent visual magnitude of the A star is -10. What is the magnitude difference? Well, the magnitude difference is m sub B minus m sub A, which is equal to -5 minus a -10. So I'm putting the -10 in parentheses. And that is equal to a -5. So a minus times a -10, which is basically a -1 times a -10, will give you a +10. So that is equal to -5 plus 10, which ends up being +5. So the magnitude difference is +5. So we're still at our +5, and we go across in our table and we still have 100. So therefore, the flux of the A star divided by the flux of the B star is still 100. Or the flux of the A star is 100 times the flux of the B star. The flux of the A star has 100 times more light coming out 1 square meter per second than the B star. Let's look at another example. So let's look at the flux. Let's say the flux coming out of the A star is 10,000 times more than the flux coming out of the B star. So then the flux of A star divided by the flux of B star is equal to 10,000. Well, let's go look at 10,000 in our table. And we come across and we see that the magnitude difference is going to be 10. So the magnitude difference is going to be the magnitude difference between the B star minus the magnitude difference between the A star, and that is going to equal a +10.